aware that anything you do or say may live in perpetuity on the internet. If you have any objections, I recommend you best leave or mute and turn your camera off. Okay, welcome. So as I said, we've got the BioEnergy Atlas team presenting to us on the BioEnergy Atlas today. Very fortunate of us, thanks team. It's going to be a beautifully choreographed interaction of 3 different speakers. We've got Dr. Hayden Wilson, who recently got his PhD. Congratulations, Hayden. Always welcome to the club.
Took long enough.
That's usually the case. It wouldn't be hard on yourself. So Hayden is a scientific program officer with uLwazi, and he is the project leader for the Renewable Energy Atlas. If I've got that wrong, then you need to correct your website. Sorry about that. We also have Dr. Marc Pienaar, who's a data scientist with uLwazi, who, as far as I understand, works on many different projects at uLwazi, but mostly with spatial data and time series data, and also enjoys working on making user-friendly applications for end users to help them explore the relationships among different data. And then we have Caroline Mfopa, who's a sparkly new member of uLwazi's data science team, who's also going to be presenting. So I'm going to ask Hayden to share his slides and start the presentation. They're going to talk for about 40 minutes, and then we'll do questions at the end. If you have a question, you're welcome to pop it into the chat box, and we can park it there, and then I'll use that to help kind of chair the questions session at the end. I'm now going to mute everyone and then ask Hayden to unmute himself so he can start presenting. So please keep your microphones muted. Thank you very much. Take it away, Hayden.
Cool. Thanks, everyone. So in this presentation, what I'm going to do is I'm basically going to walk all of you through the BioEnergy Atlas and what we're trying to achieve with this atlas and how we're going about transforming data into something that is hopefully useful for society. So the first thing you need to understand is, why is there a focus on bioenergy at all in South Africa? And the reason for this is complicated. The first reason is because South Africa is largely dependent on coal and imported crude oil. And so that means that we can't really supply ourselves particularly well, particularly from the crude oil perspective. We've got lots of coal, but oil's an issue. There's also a global drive to implement green energy options with lowered carbon emissions. And the knock-on consequence of that is that obtaining finance for big infrastructure projects that emit carbon is becoming increasingly difficult. And I'm not sure if you guys have noticed, but South Africa has a bit of an energy crisis at present, and the government is battling to obtain the funding required from international funders to meet those energy requirements. So an obvious thing to do is to go with renewable energy sources such as solar and wind, which is great for doing things like supplementing electricity supply, but it doesn't sort out our reliance on petrochemicals. We can have as much electricity as we want, but until electric cars and so on are affordable, we're going to be relying on petrochemicals for transport. And so the government sees the bioenergy industry as a potential way to sort out, or at least alleviate some of the symptoms of this reliance on oil. And they also hope that it'll do things like stimulate the economy by providing jobs. So what is the BioEnergy Atlas in a nutshell? Basically, what we're trying to do is we're trying to create a decision support system for the bioenergy industry in South Africa. So what we're doing is we're providing information on the feedstocks. So this is the raw material that will be used for bioenergy production. And it's obviously got a spatial and a temporal component to it. We're also providing information on South Africa's energy infrastructure, what exists currently. Then what we're doing is we're providing logistical information. So things like how much does it cost for you to transport materials from one place to another? What are the costs of different harvesting modes and so on? Then what we also have is a repository of information on current conversion technologies. So what a conversion technology is it's what gets used in order to convert a raw feedstock into a bioenergy product. And then what we're also providing is modeled results of techno-economic feasibility analyses. And those all get wrapped up in some detailed implementation case studies, where what we've done is partner with some stakeholders to provide them with specific information. And then we are going to be providing them with project support and then publishing their work as a case study on the Atlas. And then lastly, the thing that I think is really useful is that we're developing tools for performing water, energy, labor, and emissions nexus comparisons. So what that means is that you can then assess the trade-offs for different technology options based on those nexes. So essentially what the BioEnergy Atlas is trying to do is it's trying to solve a problem. And the problem is, how do we tell which combinations of feedstock, conversion technology, and location is feasible for bioenergy production? Now, what is feasible is variable, and it's hugely competitive in South Africa, and it's dependent on things such as oil and coal prices. So things like the recent drop in oil price, where oil price actually went negative for a while, has huge implications on whether or not a bioenergy conversion technology is feasible. So a feasible bioenergy option needs to be able to compete with existing energy sources. And if it can't, then at least we need to have some way of being able to measure how much subsidy is required in order to make that conversion technology feasible. So process technologies, which I mentioned earlier, convert raw feedstock into fuel sources. So this diagram on the right-hand side is a simplified version of all of the different processes that you can use in order to create bioenergy products. So you're taking biomass sources such as agricultural waste, energy crops or crop residue from the forestry industry, as well as industrial and domestic wastes. And then there are a whole bunch of different conversion technologies such as anaerobic digestion and pyrolysis, etc., which can be used in order to create these different bioenergy sources, which can then be used for doing things like powering vehicles, creating electricity, producing heat, and so on. So the way that we're assessing feasibility is based largely on the cost of bioenergy production. So each bioenergy option needs to be compared to a competing energy source. And the way that we're getting that unit cost of production is we are taking the cost of feedstock harvest and transportation, as well as the production cost. So, how much does it cost for you to convert your bioenergy product your feedstock into a bioenergy product? And then finally, what is the cost to transport that bioenergy product to market? And so for each candidate location in the country, we are calculating these three metrics in order to get a unit cost of production for that candidate facility. So that kind of boils us down to the logistical information that we're providing. So the logistical support that we're providing is in the form of feedstock harvest costs. So how much does it cost for you to clear a certain area and produce and use that feedstock as a bioenergy source? How much does it cost for you to transport that feedstock from where it's currently located to the closest road? And Marc's going to go into a lot of detail about how we did this later on in the presentation. And then what we have is that once you've got your feedstock to roadside, what is the cost of transporting that feedstock to the facility? And then after it's been processed at the facility, what's the cost of transporting that energy product to market? And in order to do that, what we're using is the NGI data set for South Africa. and we've processed it in order to make it useful for these kind of routing type algorithms. So determining feasibility is an interesting one because there's an economy of scale associated with these different conversion technologies. So if you look at this graph on the right-hand side, what you'll see is that when you are converting low volumes of feedstock, the cost of manufacture is quite high. And then because bigger facilities tend to be more efficient, the cost of producing that unit of technology drops with the size of the facility. However, there's a converse issue which you have to deal with, which is that small facilities don't need a lot of biomass, so the cost of transporting your biomass to that facility is low if the facility is small. But then, as the facility gets bigger, you need to go further and further away from the facility in order to get your biomass, which means the unit cost of transport climbs. So for each location and each conversion technology option, and for each feedstock source, there actually exists a lowest point where unit cost of production is lowest. And then that lowest point is the most feasible option for bioenergy production at that location. And from that, what you can do is okay, sorry, I've gone a bit far. I'll deal with that later. So the different components that we used for assessing feasibility are, we first calculated a theoretical potential, which is basically where is the feedstock and how much of it is available at each location. Then what we did is we applied technical exclusions. So for instance, we didn't assess feedstock that was within conservation or protected areas. We didn't assess feedstocks that are within military bases. We avoided feedstocks that were on steep slopes where harvesting is expensive, and so on. I've spoken a bit about the logistical and cost stuff, and I've also spoken about the conversion data, and then I'll go into some detail about feasibility later. But then after you've done the feasibility analysis for each candidate location, what you can then do is you can then assess what the impact of that is on the surrounding area. So you can do things like calculate what the greenhouse gas emissions are. We can calculate how many jobs get created. Does the project at that location meet people's requirements for social justice? What are the environmental impacts? Those are all important parts of assessing feasibility. So I'm now going to hand over to Caroline, who's going to talk a bit about how we're characterizing biomass feedstocks in South Africa.
Good afternoon, guys. My name is Caroline. I will be talking about the three main components that are found in the BioEnergy Atlas that we looked at. So firstly, I will be looking at what drives the feedstock availability in South Africa. Secondly, I will be looking at the feedstock that we assessed in the BioEnergy Atlas. And thirdly, I will be looking at how we characterize the feedstock that we have assessed. So firstly, what drives the feedstock availability in South Africa? As we all know, as a result of the global population increase, energy consumption, and the frequent natural disasters, drawing more and more attention on the future of our sustainability, our natural resources are at risk. So one of the key components that drives feedstock availability in the country is the net primary productivity. So the net primary productivity is known as the measure of the net amount of carbon assimilated after photosynthesis and autotrophic respiration over a given period of time. So the NPP can be measured in mass of carbon per unit area. So another key factor that is also affecting the NPP is the land use structure. As we all know, the land use structure is a highly dynamic process. So with an increase or a decrease of the land use structure. It will also result in the gradual increase or the decrease of available arable land and also available water resources that are available that also help perpetuate feedstock growth. Next slide, please. Okay, so the third factor that we'll be looking at is the factor of temperature and rainfall. So as we all know that areas with increased temperatures and increased rainfall are more susceptible to plant growth or feedstock growth as such. So that is also a factor when we are assessing the availability of feedstock in the country. As you can see there on the coast, the increased temperature and rainfall patterns result in the increased NPP, therefore resulting in an increase in feedstock availability in the country. Next slide, please. Okay, so the second factor for the second factor that I'll be looking at will be assessing the anthropogenic determinants, so human-induced determinants that affect the feedstock availability. So firstly is the storage and liquid waste, and secondly is the garden refuse, and thirdly is the used cooking oil that can also be used in the production of biofuel. So in the BioEnergy Atlas, we have the used cooking oil feedstock, in which Hayden will speak more about in depth later in the presentation. Next slide, please. Secondly, so we will be looking at the feedstock that we assessed in the BioEnergy Atlas. So we characterized our feedstock in 5 individual groups. So we have groups of oil, groups of agricultural waste, biomass, and also purposefully cultivated crops. So all the feedstock that you see there that are highlighted in green are the feedstock that we are revising in the current BioEnergy Atlas. So these are the critical feedstocks that we will be looking at in the atlas that we are about to produce recently. Next slide, please. So how did we characterize the feedstock availability in the country? So the characterization process the characterization process that we assessed over a 25-year planning period under current exploitation scenarios. So we looked at the spatial availability of the feedstock, we looked at the temporal availability of the feedstock, and we also looked at scenario planning. So firstly, spatial availability. We looked at where the biomass was located and what are the different conditions in the areas where these biomasses can be found. And by temporal availability, as we all know, crops and feedstock are also seasonal, so you can find them in different seasons. So we looked at the interchange of the feedstock growth in between these particular seasons. So that is the temporal availability, and we also looked at scenario planning. So what do I mean by scenario planning? So sugarcane is the leafy residue of sugarcane is typically burned. So an alternative scenario to this, when we look at scenario planning, is that we use the leafy biomass of the sugarcane for bioenergy production. So we looked at those particular scenarios and how we can change those particular scenarios in order to generate bioenergy or biofuel in that regard. So I will be passing over to Marc, who will be telling you guys about the minimum cost path algorithms that we use in our routing models in the BioEnergy Atlas. Thank you.
Good morning, everybody. My name is Marc Pienaar, and this part of the slide shows about the creation of the virtual road network for the BioAtlas. Basically what this meant was to generate a virtual road network from points in the landscape where no roads exist to points where to the closest road by navigating through a cost surface and avoiding obstacles like rivers and dams and cliffs, etc. In order to assess the feasibility of transport for biomass and or other variables. So at its core is the pathfinding algorithm, which means I have essentially broken this part of the talk into 2 parts, an overview of minimum cost path algorithms and then the methodology that we used in the BioAtlas. So a pathfinding algorithm comes out of graph theory, or it's most widely studied in graph theory, and its objective is to find the optimal route from a node in a graph to another node by navigating along the edges that connect a graph. The most practical variant, however, is something called Dijkstra's algorithm, which is a weighted graph. In other words, it's the minimum cost according to the sum of the weights of the edges from one node to another, while at the same time avoiding obstacles. So I guess you could think of this like your navigation system on your phone or something like that, where you have to navigate from some city to another city, and you choose the parameters if you want to go on a dirt road or a sand road or a tar road or something like that. Now, luckily for us, it's possible to represent these graph and tree-like structures as grids, which means each cell represents a node ID, and the values in each cell represents the weights along the edges that connect the graph. And obstacles simply just don't get values, so you don't have to assess them. Next slide, please, Hayden. Okay, so there's lots of pathfinding algorithms that exist which try and optimize the shortest path problem in terms of reducing the search space. Two of the most common ones are breadth first and depth first, if you look at the figure at the bottom left. Basically, breadth first assesses all the leaves of a specific branch in a tree, as it were, or all the adjacent cells first before moving on, whereas depth first goes down an entire branch, backtracks, and then goes down another branch. So in this little example, they both use the same amount of steps, but the depth first found its target first. It would have been reversed, I would imagine, if the source and target destination were closer together. So the time complexity of these sort of algorithms is linear, or O node plus edge, and the size of the application will simply scale linearly. However, if you start putting values into this graph or into this grid, all of a sudden the time complexity becomes O n squared, or a lot longer, quadratic in other words, which means you've got to essentially assess every single cell against every other cell to make sure you've got the actual minimum value. Now, there are ways to optimize this as well, usually through greedy algorithms. The most famous is something called A*, which was developed for robotic navigation around a room, but it's commonly used in big computer games nowadays. And what it does is it uses a heuristic, something like a distance metric, a Manhattan or a Euclidean distance or something, to direct the search from a known start to a known endpoint. The other way, of course, is to use dynamic programming. And next slide, please. The most common and well-studied dynamic programming example in graph theory is Dijkstra's algorithm. So I've borrowed this slide and hand-drawn it from that YouTube video clip. I won't go into the details of how the dynamic programming side works, but it's sufficient to say that it generates an array of unvisited and visited nodes, iterates through the unvisited and updates values in a table while calculating the algorithm until the unvisited array is depleted. What's important is the way the output is generated. So if you look at this table, this is the typical output of Dijkstra's algorithm, where there are three columns. The first column is all the nodes that exist in the graph. The second is the distance from a start node to all the other nodes. And the third is what was the previous vertex or node that was visited. So looking at the red path, which is highlighted from A to C, we can look up C in our table and see that the distance is 7, which makes sense. It's 1 plus 1 plus 5. And if we want to derive the path, we can also do it from this table. So we see what, working backwards that is, we start with C, look what its previous node visited was, and that's E in the table, that is. Then we go to E in the table, see its previous node was D, and then we go to D and see its previous node was A. And thus we have derived our path. So very nice, efficient, and simple algorithm. And hopefully that's enough background on these kind of pathfinding algorithms to go on to the next section. Okay, so this I've also subdivided into two sections. The one is the creation of our inputs and our cost surface, and the second is the actual methodology we used in the BioAtlas. Next slide, please. Okay, so for our cost surface, we used a DEM, which is a digital elevation model derived from NASA's shuttle radar topography mission. It comes in images that are roughly 1 degree by 1 degree, 3,600 by 3,600 pixels, more or less. There's over 150 of these that make up South Africa. So if you put them together and merge them into one giant image, you get the equivalent of about 2,700,000,000 pixels that we need to navigate through. Okay, then we took this cost surface and we burnt in all our obstacles. In other words, we removed the values by burning in big dams, rivers, lakes, military bases, slope values that were too expensive to assess, etc. For our source and destination points, the destination points were made up of the NGI road network, which we burnt into the cost surface to get a point layer because it comes as a line layer. So we get points that are roughly 30 by 30 meters apart, which is the horizontal resolution of our DEM image. And for our source points, we generated a 1 by 1 kilometer point network using StatsSA's basic spatial planning unit grid. So the reason I've highlighted these large numbers in red is because if we were to brute force a virtual road network through this cost surface, it means for each 1.2 million or so source points, we'd have to iterate through the 2 billion or whatever pixels and find the 60 million destination points and then assess the shortest path for each source and then repeat for each 1.2. Or to put it in other words, not possible with our current computing technology that we have at least. So we had to come up with a way to chunk this or do it in smaller sections. Obviously we can't, sorry, go back a slide. We can't use one of those tiles, which you see in the close-up view there, because if a source point was close to an edge, for instance, we wouldn't know if the closest road is an adjacent tile that we're not busy analyzing at the moment. So we had to come up with a different methodology. Next slide. Okay, so this is the methodology, and hopefully I can try and explain it in some meaningful way. What we did was we took the source points and extracted a large cluster of these, say 30,000 at a time. Those are the purple highlighted dots in figure 1. Then we throw that cluster into our algorithm, figure 2, and the algorithm takes the Euclidean distance from our starting point to all other points and then ranks them and takes the first 200 or 250. So I think I use 250 points at a time. Those are those yellow highlighted ones closest to the top left point. Matrix, which is 250 by 250 or whatever our n size is, we can merge those and create a shapefile to get the extent of our analyzing window. That's 0.4. So once we have an analyzing window, which hopefully covers the roads that we need to find, we then do the cost algorithm. For the cost algorithm, you start at a point and you normalize the grid. In other words, you take the value at that grid, which in this case will be altitude, and you subtract all the remaining cells from that and take the absolute value so that uphills and downhills are equally weighted. Then you also have to add the horizontal resolution to minimize the vertical bias, since the horizontal is roughly 30 meters and the vertical is in 1 meter units. Work out the paths to all of the destination points in the analyzing window and find the shortest one. And those are what those little blue lines are. Those are the shortest paths from those points to the road network. Okay, then in step 5, we take those 250 points that we've just analyzed and buffer them so that we can take the difference between our current source centroid layer and extract them from future analysis, kind of similar to that dynamic programming idea of Dijkstra's algorithm, and then simply repeat 2 to 4, steps 2 to 4. So in image 6, that's exactly what happened. That's our next analyzing window, and it shows how much of an overlap there is and why we had to develop this kind of variable window approach where the red dots are the new centroid points. An important point here is that if you don't normalize the cost surface, you end up with a river routing algorithm because you're just going to go downhill because those are the minimum values, depending on the resolution of your DEM, of course. Next slide. Okay, so that's basically it for me. Hopefully it was a good enough overview. That rainbow image of South Africa is the kind of chunks of points that were analyzed, but what it's actually representing are all the little paths. So if you backtrack down to the top left, you'll see like a zoomed up image of all those little paths creating the virtual road network. And of course, you can take these values and turn them into a geotiff or a Rust or something like that, which is the bottom left, given in meter units. I'll now hand over back to Hayden to continue. Thank you very much.
Cool. So after the feasibility analysis has been performed, there are a number of outputs that get generated from the modeling process. So the first thing that we've got is that we've got feasibility tested conversion scenarios for each candidate location. And then what we also have is costs of producing alternatives, because we've assessed about 32 different conversion technology options for each candidate location. And we've selected the cheapest one. But then what you can do is you can say, okay, we're not interested in going with the cheapest option. We want to produce something else. Then you can compare the two and get a difference. And then because the conversion technologies have got metrics around them for emissions and labor potential and so on, water use for each technology option, we can then calculate that for each candidate facility location. So this map on the right-hand side shows you what the output of the modeling process basically looks like. So each of those is a catchment for a particular facility, and then the dark blue blobs are the areas where the cost of production is cheaper, and then as you go further out, it becomes more expensive. So the interesting thing about the fact that we've taken this approach of harvesting these additional metrics other than just cost, it means that you can perform Nexus comparisons. So essentially what we can do is we can say, okay, for each given location where bioenergy production is feasible, we take the lowest unit cost of production, the technology option with the lowest unit cost of production, as being the baseline. And then what we can do is you can start adding management objectives on top of that. So for instance, if your management objective is job creation, what you can then do is from the list of pre-calculated feasible technology options, you can then say, okay, at this location, the one that maximizes job creation is this technology. And then what you can do is you can compare the job creation option to the one with the lowest unit cost of production. And then the difference between the two is essentially the cost of your management objective. So what this enables you to do is calculate trade-offs based on an optimization for one or more of these different objectives. And I think that's quite a powerful thing for people in the planning space in South Africa, because now it means that decisions are no longer arbitrary. It means that you can say, okay, we want to optimize for saving water, and you know what that's going to cost. And what's interesting is that because we have information on the cost of different renewable options, you can then say, okay, well, this is the lowest unit cost of production, but honestly, it would be better for you to spend your money on something like a solar farm at this location if your objective is energy output. So that's why the ability to perform Nexus comparisons is really important for the BioEnergy Atlas. So how do you actually assess these alternatives? I've kind of gone into a bit of detail about it, but essentially what you do is you produce a graph similar to this, where if you have a look here, you'll see that each of the dots represents a technology option. The color represents whether or not that technology option is currently mature enough to be implemented. So the white ones are essentially ones that are still in an R&D phase. Then what you've got is you've got these lines which represent the cost of different alternative energy options. And so then you can see that bioenergy options that fall below a particular threshold are the ones that are competitive against that alternative technology option. So how does the BioEnergy Atlas actually help society? Why are we going to all this effort? So one of the things that the Department of Science and Innovation, who are the funders for the BioEnergy Atlas, have specified is that the BioEnergy Atlas needs to provide implementable support. You know, we need to be able to show that we're having an impact with all of this money that they're throwing at us. So one of the things that we've done is we've partnered with specific projects and industries to provide them with support. One example project is the Women in Biodiesel project. Now, that project aims to equip 10 women-owned businesses, basically one in each province, with a small business that takes used cooking oil and converts it into biodiesel that those women can then sell. Now, that's essentially solving a couple of problems. Firstly, it's meeting all sorts of social justice objectives. And secondly, what it's doing is it's it's reducing the reliance on fossil fuels. And thirdly, it's preventing the sale of used cooking oil to secondary markets where it could be dangerous. So currently a lot of South Africa's used cooking oil, which has been shown to be carcinogenic because it's been used so much, actually gets sold to our neighboring countries such as Mozambique, where it still gets used for cooking. And so providing an alternative market for this sort of thing is definitely a worthwhile activity. Another project that we are involved in was the Waste to Wing project. Basically, Waste to Wing was a collaboration between SASOL and the WWF and a business acceleration organization called FATOLA, where what we did is we assessed whether or not it would be feasible to use alien invasive vegetation as feedstock for aviation fuel in and around Sasol's Secunda, what is it called? Yeah, factory. And basically what Waste to Wing showed is that it was feasible. However, Sasol were not willing to engage with the technology further, unfortunately. Our work with Waste to Wing also led us into working further with the WWF, where what they've done is they've partnered with an organization called the Roundtable on Sustainable Biomaterials. And what they're doing is assessing what other feedstocks in South Africa could be used to provide sustainable aviation fuel. And so one of the big ones that we've recently helped them out with is characterizing sugarcane availability in South Africa, as well as the costs of transporting it. We're also involved in a working group with the Department of Environment and Fisheries and Forestries, as well as the Dutch government, on developing a knowledge platform for bioenergy in South Africa. SAEON is essentially going to be the point leader on things like biomass availability. And then the Dutch government is going to provide additional information on conversion technologies, as well as information on potential international people that could buy biomass from South Africa. Then another thing that we're involved in is the Renewable Energy Independent Power Producer Program, where the idea is that the BioEnergy Atlas is going to provide the procurement people for REIP with information as to which technology options are feasible where, which will optimize their processes. And then we're also in discussion with DINIM and on the Working for Water program to provide them with assistance in terms of what value-added products can be derived from the invasive vegetation that they're clearing. The idea being that the subsidy from selling biomass could pay for the clearing of more alien invasive vegetation. So that's our project support. Then what we're also working on is a thing called the District Decision Support Tool. And basically what that is it's we're providing these different feasibility tested scenarios in a tool which enables district planners to understand what options exist for job creation from bioenergy for their particular district. So they would be able to select a district from a map, and then you get all of the different feasible options there, and it enables them to assess the trade-offs. Then what we're also doing is we're trying to foster collaboration and communication within the bioenergy industry and within government. So what we've done is we've created a public database where people will be able to register their organization and the types of activities that their organization performs, with the idea being that you can then create synergies within a particular area. So for instance, if you ran a small company that, did things like clear a lot of garden refuse, and you knew that there was another company existing in your area that might be able to sell that biomass and chip it and export it, being able to search for organizations that are operational within your area within the atlas will facilitate that sort of collaboration. So yeah, that's what we're trying to achieve with the BioEnergy Atlas. Does anyone have any questions?
Yeah, thanks, team. That was a very nice overview of what you guys have been up to. A little bit for everyone, a little bit of the serious data science, a little bit of the more social context. It was a very nice overview. So does anyone have any questions? I don't see any that have popped up in the chat box, but maybe there is a raise hand function if you have anything that you would like to question, or if you can't find that, just pop something in the chat box to say you'd like to ask a question. Otherwise, I have a couple, but my questions are usually nasty, so let's start with someone else. No one?
Go for it, Jasper. I'm ready.
Okay, here we go. And this is a bit unfair because this is always the question that comes up with the talk of use of bioenergy, which is essentially the trade-offs with other land use and other priorities. A lot of the feedstocks that were talked about were agricultural crops. And that means you've got a trade-off in terms of land cover, in terms of space for growing it, but then also a trade-off with food security potentially. And I was wondering to what extent you guys are exploring that or planning on exploring that, or is that just way too big and beyond the remit of the project?
So the way that we're dealing with purposefully grown crops and specifically food crops is with food crops, we weren't assessing the actual, you're not going to say, can you use corn, for instance, for as a bioenergy feed source? What we did is we said, okay, what's the availability of residue from the corn industry that can be used for bioenergy production? So that's the idea, is that if it's a primary food source, then we're not assessing it. However, there is an exception with that with the sugarcane industry, where I don't know if everyone's aware, but the sugarcane industry in South Africa is in crisis because of the fact that there's been a major shift away from using sugar inside things like soft drinks and so on. So we were specifically told that we needed to look at sugarcane as a way of trying to assist the sugarcane industry in South Africa, because it supports so many people and so many jobs. But again, there what we've done is we've worked with scenarios. So scenario A would be business as usual. Scenario B would be using subsistence farmers to produce sugarcane on their land. And scenario C would be commercial forests, commercial operations, selling it and so on. But there are always downstream impacts which are really difficult to characterize in this sort of way. But I think it's better to take a stab at it than simply leave it up in the air and it never comes to light.
Yeah, I think with the sugarcane example, I'm not sure if you're aware of what's happening in Reunion Island, but they actually power a lot of their energy is from sugarcane. And interestingly, it's actually from the residue from sugarcane. So I think the normal practice here is to burn the field standing and then just harvest the stems. But what they do in Reunion is they harvest the whole plant and they strip off extra leaves, and that gets used for the energy production, and the rest goes to sugar production. So in a way, there's a win-win there potentially. But obviously, you need to know more about how they farm sugar and process it and stuff to know if it's true or not. I don't know the details.
No, it's absolutely correct. So that's the that's one of the scenarios that we've modeled. So what with the sugarcane industry, they do. So it's interesting. So the lower part of KwaZulu-Natal, they burn it, but then at the top near Richards Bay, they seem to be shifting over to not burning and leaving the leafy and brown leaf biomass in field. And then what we've also had to do is we've had to assess, what are the options in terms of soil fertility. What is a safe amount for us to, what can you safely remove for bioenergy production without impacting soil fertility? And we've had to do that for the forestry industry as well. So at present, what they do is during harvest, forestry companies only really want the stems. They're not interested in any of the stuff around the tree. So they'll leave the tops and the bark and the whole bunch of stuff in field, with the idea being that it'll improve soil fertility, but then it presents a massive fire hazard. So what a lot of forestry companies do is controlled burning of their forestry residue. And obviously that's a CO2 disaster. And forestry companies are quite interested in not doing that because it reflects really badly and from a carbon tax perspective. So we've commissioned an organization called the ICFR to assist us with calculating, what is the sustainable threshold for forestry production in South Africa, bioenergy production from forestry residue in South Africa without impacting soil fertility.
Genevieve had a question about who are the biggest users of the bioenergy atlas, or the envisioned biggest users, I suppose, if the website isn't up.
So that's a tricky one, because we have a variety of stakeholders that engage with different levels of data. So the idea is that we're providing information for SMMEs who want to know, I run a biomass clearing business, where's a good place for me to go and do this thing? But then what you also need to do is you've got people that want to invest in different bioenergy production technologies. So, a good example would be an organization called uLwazi, who are thinking of rolling out a massive biomass chipping plant down in the Eastern Cape in order to sell the pelletized biomass overseas. And so they would be using our data for a lot of their modeling and assessments. And then another user would be government, with the idea of then being able to know what sort of technology options do they have to sort out their energy issues as well as create jobs and so on.
Cool. I have another really tough question for you. So the one thing that I've always wondered about with projects like the BioEnergy Atlas, but also with kind of carbon sinks and Sava and so on, is that they involve a lot of science, but they're not really science projects per se. In that they're more like a consultancy report, and making that kind of information available. But are there any things in place or plans to do a kind of peer review of what has been done and whether the various components of the projects are kind of up to scratch, but also on the other side of things, the work that's been done can in itself make for a great scientific publication. So are there plans to write it up for publication?
So absolutely, there are plans for writing it up. I think Marc and I are really planning on doing that routing algorithm as a paper, because that windowed approach is really interesting. Then the process technology, the ways of assessing feasibility from a logistical, from a spatial logistical perspective is also definitely worth a paper. And then the forestry residue availability data sets and some of the stuff on feedstock availability is also, I'd say, publication worthy. And the plan is absolutely to publish it. Then what we're trying to do as well is with the processes that we're using in the atlas, things like when we're generating these maps of the availability of different feedstocks and we're making assumptions around transportation costs and that sort of thing, what we're doing is we're engaging with the subject matter experts for those particular facets. So for instance, all of our process technologies come from peer-reviewed journals, and we're also in collaboration with the University of Stellenbosch to assist us with that. So that kind of provides a certain amount of rigor. And then ditto for the forestry residue, we've partnered with the ICFR, who are South Africa's the repository for information, and we've partnered with SASRI for the sugarcane information. So what we're trying to do is kind of peer review as we go and bounce stuff off as many experts as possible, so that and it's not just a case of us sucking something out of the blue. We've engaged with Glenn and you on alien invasive vegetation, for instance, and we're kind of taking things iteratively as we go.
Yeah, I should think.
But it would be nice to have more of an oversee, like a committee to oversee this sort of thing. I think. But the problem is how do you identify who are the experts and then get them to all actually do what you want them to do is also not simple.
Yeah, for sure. I suppose one thing, there's just if you make sure that the methods are well described and available is one component, so that people can at least assess for themselves if there are things they should be concerned about. I have Genevieve has raised her hand. You want to unmute and ask us a question, Genevieve, or is that yeah?
No, I'm happy to unmute and ask. It's so exciting to see this is happening. But so I personally think that what you were speaking about, the fostering collaboration with those smaller, where you create the synergies with people and small businesses that are already. How would one access that? Like, where does one find that collaboration platform?
So it currently exists on the new BioEnergy Atlas website. So what you would do is there's a thing called a tab called the BioEnergy Atlas Company Register. And when you go to that register, the first thing it does is it provides you with a map that you can then search for various organizations that are operational within your area. And there's some filters, which mean that you can, filter according to what the different organizations do. And then what there is there's also a form which you can fill in to register your company or organization's details. So
how is that getting put out there? Is like, how are we putting that to the market, by the way?
Currently we're not. The idea is that once the website actually has some content available to it, what we'll do is do a focused stakeholder campaign. So the DSI have obviously got their mailing lists of various people that are operational within the space. Department of Environmental Affairs have through NRM have a lot of engagements, and we also have engagements with the Dutch Knowledge Platform crowd. So the idea is that once the atlas actually looks like something, then we'll spread it far and wide and say, please register your details with us.
Very exciting.
And hopefully that will be enough. But if anyone has any suggestions as to better ways to do this, please let me know.
Thanks, Hayden. Yeah, I don't know, Marc or Caroline, I don't know if you have anything to add. I haven't really drawn you into answering the questions because I didn't want to put anyone on the spot. But if you have anything to add, then by all means.
No, I'm happy to sit in the background, to be honest.
Yeah, I think Hayden has pretty much answered everything that everyone wanted to hear. Yeah, I think we covered up everything.
Cool. Well, then I think all that remains is to thank our speakers. I think it was a very informative talk. And thank you very much for stepping up at the last minute to fill the gap in our schedule. You can all give them a virtual round of applause. And then just to say, our next speaker will be on the 2nd of October. It's going to be Olisa Dlomo from uLwazi. And I'll circulate an ad about his talk, but it'll be, at least his initial suggestion, it'll be to do with spatial upwelling indices in Algoa and St. Francis Bay. So thank you very much and see you next month.
Cool. Thanks for listening to me, everyone.
Cool. Cheers.
Thank you, Marc.